Okay, everybody, welcome to IMSE881 Linear Programming, Lecture 2. Today we're going to start talking about uh, some of the first example for your linear programming. And this set of slide is from the handout page from 1 to 21. Uh, we're going to review some of the linear algebra concept related to linear programming as well. So we're going to review some of the, freshman, sophomore linear algebra for that purpose. And for undergraduate students who had a degree in here, we'll pretty much review some of the concept we learned from the matrix theory class. First, we're going to introduce a linear programming problem models. It's a maximize for x1 plus x2, and the constraint is 3x1 plus 4x2 is less than equals to 15, and 10x1 minus 2x2 is less than equals to 9, and both x1 and x2 are non-negative, are greater than or equals to 0. And for this type of thing, we're going to convert it into a standard form of linear programming by adding a slack variable, x3 and x4, and using them as an initial basic variable solution. And so initially x1 and x2 are equal to 0, and x3 equals to 15, and x4 equals to 9 in that case. Um, and also, the cost coefficients for x3 and x4 are equal to 0. So therefore, they're not affecting the final optimal, the objective function value. Doesn't matter. So initially they are 0, and we're trying to maximize it. And we basically willing to introduce x1 and x2 into the solution so we can maximize the objective function. Okay, this is one of a form of a linear model. Let's look at the other ones, and this one is a minimization problem with a 3x1 plus 5x2. They're minimizing these. However, x1 plus 2x2 has to be greater than 10 or equal to 10, and 3x1 plus x2 should be greater than or equals to 8. Both x1 and x2 are non-negative. And this by adding a so-called surplus variable, x3 and x4, and with a negative sign. So this will change the greater than or equals to constraint into an equality constraint or equals to constraint. However, here, since x1 to x4 are non-negative, we cannot easily get an initial basic solution or feasible basic solution. So what we do is we adding two artificial variables, a1 and a2, and this a1 and a2 can be initially be equals to 10. I set x1 to x4 equal to 0 to begin with, so a1 equals to 10. And same thing, a2 equals to a in the very beginning. So we get a initial basic feasible basic solution, and also see how we're going to change the objective function term. So x3 and x4 still getting a coefficient of 0, so they have no impact on the overall objective function. However, we're going to, since this is a minimization problem, we're going to penalize these artificial variable inside my basis, inside my solution. So if a1 and a2 are greater than or equals to 0, and then these capital N represent a huge number, okay, represent any large number. So this will not be the optimal solution. So we force in the optimal, and a1 and a2 are out of our solution basis. Many of these are actually uh, conventional technique and trying to find the initial basic solution, however, not impacting the overall objective function at the end. Okay, so this is an illustration, a graphical illustration of the first problem as a maximization problem. And these are the two constraints I have. 3x1 plus 4x2 less than equals to 15, and 10x1 minus 2x2 is less than equals to 8. So these are the two constraints, and also x1 and x2 are non-negative. And the red dot line represent the objective function level, so x1 plus x2, since we're trying to maximize it, so this line is going to be moving forward, moving up like this. The other case is the second example problem we have is a minimization problem. And the first equation is x1 plus 2x2 is greater than or equals to 10, represented by this constraint, this area. And also the second constraint represents 3x1 plus x2 greater than or equals to 8. And this is my, the green area is my feasible region. And then the red dot line also represents the objective function, since we are minimizing, so this line is pushing as low as possible. So this is this point, intersection of these two constraints, will be the optimal solution. The last point when this level set of the objective function leave the feasible region. On the other hand, you can see that this for the other maximization problem, the start line moving upward or to the right until it leaves the feasible region, and this will be the point actually finally leave the feasible region, and that will be the optimal solution for that problem. We'll talk about more detail, but here we just want you to illustrate it to you. How can we represent graphically for two-dimensional problem, the feasible region, the objective function, level set, and so on and so forth. There are two types of feasible region, like we said. One we call the unbounded region. Unbounded region is all the constraint you have, so representing the feasible region, you have an open area, and that's in the similar direction for your objective function. So if the objective function is moving this direction, you can move this objective function value to the infinite large, okay? However, if the objective function value is minimization, is moving the opposite direction, and this will be your last point, leaving the feasible region. So you can see it depends on the direction of the objective function, either maximization or minimization. For a closed, we call it bounded region, is much simpler. Doesn't matter is maximization or minimization. You can see that if the objective function move, it actually will leave to touch a corner point, or we call the extreme point of this feasible region if the region is bounded by all constraints. So there is no infinite horizon. So these are the feasible region description we have. We're going to come back to further discuss the mathematically, what are the conditions you have an unbounded objective function solution, or you have a bounded solution. Okay, now we can actually more put a linear programming model in the more formal term using linear algebra. The minimized an objective function is the summation of Cj times Xj. Cj is the cost coefficient for your model, and this is the objective function, and subject to a whole bunch of constraints, total of m constraint right here. And aij times xj equals to bi for I equals 1 to m. So we have m of those constraints, and aij usually we call the cost coefficient for each one of the constraints. And by default, we're assuming all the decision variable xj are non-negative, which is greater than or equal to 0. And total, we have n of those decision variable. We can put this into matrix form, and minimize C transpose times X is the objective function equivalent to summation of Cj times Xj up here. And we can represent this m of these constraint in an m by n matrix is Ax equals to b is actually a linear system. Of course, the x are non-negative. Here, C transpose are a row vector. We could represent C1, C2 all the way to the Cn. X is n by 1 column vector, and B is m by 1 column vector. The A matrix is m by n matrix. So here, throughout the semester, if we not specifying all the vector, we are specifying our so-called column vector by default. Okay, they are all column vector by default. So you can see that C transpose will be a row vector in this case. The application for linear programming are many aspects, and is most popular model optimization model used in the industry. The most classic application example is the animal feed mixture mix formulation, and this is referred as a classic blending problem. You have several different feed ingredient. You trying to mix them to create a blended feed for the animal, either chicken or cattle. And each one of the ingredient has a different nutrition content. And in order to satisfy the animal's nutrition need, and your feed has to satisfy certain nutrition level, but you also want to minimize the total cost for for your mixture. So what would be the optimal, which is has the lowest cost but satisfying all the nutrition requirement? And second category of applications called cutting stock problem. Usually the cutting stock problem is trying to minimize the waste of materials. For example, this is cutting wood into smaller pieces and sell the for customer order. And sometimes it's a paper roll, a huge roll of paper, and you trying to cut a certain width to sell it to different customer. And textile industry also use. And the cutting stock problem also fairly common in the parking in the loading dock in the seaport, seaport. And these are fairly standard application for cutting stock problem, and they have a very famous values in various industries. The third most popular model application for linear programs, either we call it transportation problem or transshipment problem. These type of problems are usually using in logistics to determine the optimal flow or fleet assignment to each shipment between the source and the destination. The source have the supply, which is usually the warehouse or the hub. And the destination usually means a retail store. We have a demand from the market. So how to satisfy those things? And the number 4 is the very classic production scheduling and the planning problems. And these are periodically a company trying to create a production schedule or plan for the next quarter or next month based on the resources, either material, the human resources, the capital budget, they have, but they trying to create a so-called product production schedule, so they can maximize their profit or minimize their certain type of costs. The capital budgeting problem is also becoming a very popular problem, and basically it's a resource allocation problem. You have, for the company has a multi offices, international offices in each branch, and the headquarters trying to have a budget issued to for each branch office for their next year's project or infrastructure improvements. So we have a fixed or limited capital. How are we going to assign it to different projects so we can maximize our outcome or revenues or profit with a limited amount of capitals what we have. The last one is more modern application called tank scheduling problem. We have a so-called trailer or tank and trying to schedule them to different location to pick up their load and deliver to the next location. So these are the more modern application. I also including some of the references below, and you are welcome to check them out. There are many real-world applications using linear programming, and in fact, the logistic company like a FedEx and UPS and Yellow Freight, they are still using linear programming model on a daily basis still. Next, what we want to do is we're going to review some of the matrix theory and linear algebra concept you learn from either from your Cal 1, before Cal 1, which is the linear algebra or matrix theory in the college. Some of you also had it in the AP classes in high school. So first, as we said, we assuming all the vector we mentioned in this class are column vector by default, and several specialized vectors are zero vector. It's a vector of 0. E sub I represents a unity vector, which is all the elements but the ith element equals to 0 only in the ith elements equals to 1. We call it a unit vector of I. 1 vector, which is the entire column vector of 1. And the column vector, usually we can represent A sub I equals to a column vector A1 to AN, B, the same thing. A plus B is basically element by elements summation for A vector and B vector. Scale multiplications is n times A equals to n times each one of the elements in A vector. Inner product, what we call a dot product, is basically A transpose times B. It represents AI times BI and sum it up together. And it's exactly equals to B transpose times A. And many times in the paper or textbook, you see that A dot B. So inner product usually referenced as a dot product. And also you see in the paper and textbook, and they using an angle bracket trying to A comma B represent this inner product. So there's various of presentation, but you know they're this inner product or dot product in a sense. The normal vector is the size of the vector represent all the elements of A, actually square, and then you sum it up together, take a square root out of it. So basically it's A transpose times A, so the inner product of A times A, and take a square root of it. Okay, so here is the equation. Actually, the norm of A dot B, which A times A transpose times B, is less than equals to the norm A times the norm of B. And in fact, this is a Schwarz inequality, and A dot B, the norm of A dot B equals to actually less than or equals to 8, the norm of A times the norm of B times the cosine of the alpha between A and B vector. Finally, the Euclidean space, we're going to mention many times in this several lecture, is E sub n, represent an n-dimensional Euclidean space collection of vector with a size of n. N means is n-dimensional Euclidean space. Okay. Next is a little bit summation of the concept you learned from before. Giving a set of vector in n-dimensional Euclidean space A1 through AN belongs to n-dimensional Euclidean space. The vector B is said to be, first, the linear combination of A if B equals to summation of lambda j times AJ. All the lambda j belongs to a real number. So this is basically a linear combination. Second, we call it affine combination. The affine combination represents B equals to summation of lambda j times AJ, where lambda 1 to lambda n is equals to R1, which is still a real number. However, we have additional constraint, which is lambda, summation of lambda equals to 1. And we're going to show you later on how these two are geometrically different. Convex combination. Convex combination is a affine combination, but we're limited. The lambda 1 to lambda m can be only non-negative number, which is r plus, which is lambda 1 through lambda n, they are greater than or equals to 0. We still have the constraint, which is summation of lambda equals to 1. And the next one is we call the cone combination. The cone combination is the convex combination. We drop the summation of a lambda, summation of lambda j equals to 1. But we maintain the lambda 1 to lambda n has to be non-negative. Okay, we will come up with the next slide to okay, now we start illustrate what is the linear combination. The linear combination is basically a real combination of two vector A and B, A1 and A2. For example, I have a two vector, okay, A1 and A2. A1, A2, two vector. And the linear combination is actually so-called, for example, x equals to, okay, lambda 1 times A1 plus lambda 2 times A2. And both lambda 1 and lambda 2 are real number. Okay, can be positive or negative. So let's look at what is, if lambda 1 equals to 1 and lambda 2 equals to 1, so what we actually have is just moving the A1 to here. Okay, A1 to here. And that's the x vector you have. I can also, using half of a negative 1/2 of A1, for example. So there's a negative 1/2 of A1, so negative 1/2 of A1. And then if I move it over here and this is another x. Okay, so it's x1, x2, we can have, or we can have a negative a2, some portion of a2 right over here. Okay, maybe negative 1/3 of a2, but we move it over to this direction, and the result will be this. So you can see that if A1 and A2 are linearly independent, basically I can represent any point on this two-dimensional space. So linear combination is when lambda 1 and lambda 2 both are real number. Basically, you spend the entire two-dimensional space. Let's take a look on the second, affine combination. Affine combination is using the same concept, but here I have one more restriction called lambda 1 plus lambda 2 equals to 1. And what happened? Let's do that. Erase most of these. Okay, if we call this guy, let's do everything again. Okay, here we have A1, A2, A1, A2. Okay, if lambda 1 times A1 and lambda 2 times A2 and lambda 1 and both lambda 1 and lambda 2 are equals to 1, basically what we have is a line across the tip of those two. So any points on this will be the affine combination passing through the tip of these A1 and A2. Okay, if we third ones, if we adding one more restriction, which is both lambda 1 and lambda 2 are belongs to the R plus, non-negative. Or we can say lambda 1, lambda 2 are greater than equals to 0 since they are scalar. So what is this part going to be? Is basically the line segment in between. That's the convex combination. Okay? The line segment in between this A1 and A2 are the convex combination. The third one is the cone combination. The cone combination basically is a little bit easier. Since you have A1, you extend the line of A1 and A2. The entire cone produced by A1 and A2, every single point inside this area, represent the cone combination. That means we drop the lambda 1 plus lambda 2 equals to 0, but we maintain lambda 1 and lambda 2 is positive. In this case, we basically produce a cone in that case. This is also true in two-dimensional, three-dimensional, and so on and so forth. So this is how we illustrate the linear combination, which is only have lambda 1, lambda 2 are real. By adding the lambda 1 and lambda 2 equals to 1, plus 1, 2 equals to 1, we are creating a so-called affine combination, which is the blue lines over here. By further restricted, lambda 1 and lambda 2 are non-negative, which is greater than equals to 0. Actually, we create a so-called convex combination, which is the line segment between A and 2, A1 and A2. If we drop the condition of lambda 1 plus lambda 2, maintain lambda has to be non-negative, then we create an entire cone section to the infinity spanned by A1 and A2. So this is it. Talk about and graphically how this relate. Next is the linear dependency we have. For example, a set of vector A1 through AK belongs to n-dimensional Euclidean space in the first sentence. S is a linearly independent if we can find a set of a lambda j such that lambda summation of lambda j times aj equals to 0 is satisfied when all the lambda are equals to 0. So we talk about this is the set of A vectors are linearly independent. We call S is linearly dependent if we can find sum of the lambda j is not equal to 0 when we represent the lambda j times aj equals to 0 using this set. Okay, so here is what we call the linear independency and linear dependency. So what is that supposed to mean? And with these two definitions, we can formally bring out the basis of n-dimensional Euclidean space is a set of n linearly independent vector in n-dimensional Euclidean space, and we call the basis of En. Example, the most straightforward example for independent bases are E1, E2 to En, where E is a set of a unit vector with with one position equals to 1 and everywhere else equals to 0.